Poonam Kulkarni from GSI Environmental.
And I'm Chuck Newell, also with GSI Environmental.
And this is one of a series of videos that highlight cutting-edge CERDUP and ESTCP R&D projects.
Now today we're going to discuss a CERDUP project that tested a new method to measure biodegradation rates of chlorinated solvents in groundwater plumes.
Groundwater contamination by chlorinated solvents like trichloroethene, abbreviated as TCE, or perchloroethene, abbreviated as PCE, is one of the most common environmental problems faced by the Department of Defense, other federal agencies, and many industrial companies. But what happens to these chlorinated solvent contaminants in groundwater, and how can we tell if nature is helping via natural attenuation processes? And if it is occurring, what is the rate of that biodegradation?
Now, underneath the Navy's Air Station North Island in San Diego is one of these chlorinated solvent groundwater plumes. Like thousands of other chlorinated solvent plumes at military bases and chemical plants, industrial facilities, and even dry cleaners, this plume was created many years ago before society figured out that the common ways to dispose of waste solvents could threaten groundwater. Now, after these contaminants were released to the environment, they formed groundwater plumes, which we now know are extremely difficult to clean up. Department of Defense CERDUP researchers are exploring better ways to understand if nature is helping destroy these chlorinated solvents in the groundwater.
Now, originally, researchers had to drill numerous groundwater monitoring wells and sample in many places over and over again to get an idea if naturally occurring bacteria were slowly destroying the TCE in the plume, a process called biodegradation. The monitoring well approach was expensive and often did not provide a clear picture about natural attenuation of these groundwater contaminants. Therefore, there's a need for a better way to understand if and how fast the chlorinated solvents were biodegrading. This CERDUP project applied a relatively new technology using radiocarbon analysis to get a clearer picture about biodegradation of groundwater contaminants like TCE and PCE.
Now, the CERDUP project, entitled Carbon Dioxide Radiocarbon Analysis to Quantify Organic Contaminant Degradation, Monitored Natural Attenuation, and Engineered Remediation Approaches. The principal investigators are Dr. Tom Boyd from the Naval Research Laboratory, and the co-PIs are Dr. Michael Montgomery, also from the Navy Lab, and Dr. Richard Cuenca and Dr. Yukata Hagamoto from Oregon State University.
The objective was to combine two things. First, to measure the amount of radiocarbon. This is actually the amount of the carbon-14 isotope present in the groundwater plume. And second, to measure the rate the carbon dioxide was leaving the subsurface, something the research team calls the carbon dioxide flux. These data were then used to estimate the actual biodegradation rate of the TCE and to help confirm where the TCE plume was located in the subsurface.
Okay, Poonam, let's go over the key findings and key points from this project.
Sure. Now, understanding the natural biodegradation rate of chlorinated solvent plumes is very useful in managing these plumes.
A new method based on radiocarbon analysis and carbon dioxide flux measurements has been developed and tested in the field.
At the test site, the method showed 90 kilograms per year of chlorinated solvents were being biodegraded naturally over the entire groundwater plume.
And that's a lot compared to the estimated 1,500 kilograms of dissolved chlorinated solvents in the plume, and suggests the plume might be largely biodegraded away in 17 years if there are no additional source materials like Dean apple at the site.
Great. Now let's go into the details so we understand how this technology works.
Sounds good.
To understand the technology, we should first familiarize ourselves with the definition of radiocarbons.
Okay, to do that, we need to go back, way back to the age of the dinosaurs, 60 million years ago, where prehistoric plants would take up carbon from the atmosphere just like they do now. And within that carbon dioxide, there's radioactive carbon isotopes, the one we call carbon-14. Now, these prehistoric plants, they would die, get buried, and leave behind these radiocarbon isotopes, which have a half-life about 5,700 years, so that after about 60,000 years, almost all of that C14 is gone. Now, remember that the hydrocarbons that form petroleum have been sitting in the ground for 60 million years or so, which means that all the C14 and this oil is long gone from these hydrocarbons.
Now fast forward to today, where we collect these petroleum hydrocarbons to produce a lot of the products we use, including our industrial chemical, TCE.
And sometimes our products find their way back underground, but this time as groundwater contamination. But interestingly enough, microorganisms love to snack on just about anything organic, including groundwater contaminants, like our TCE plume at a North Island. This is called biodegradation, where bio means a biological organism is degrading the chemical through digesting it, just like a yummy cupcake.
And after the microorganisms have chowed down on the TCE, what's left is carbon dioxide. If that carbon dioxide has no radiocarbon in it, that means it's very old carbon, at least 60,000 years, and when we can assume that this carbon dioxide came from a hydrocarbon. On the other hand, if the carbon dioxide has radiocarbons in it, then it's young carbon, and we can assume that carbon came from a natural source, like grass clippings.
Now, we just have to get the carbon and analyze it for carbon-14. Sampling for carbon dioxide is cheap, and the radiocarbon analysis will tell us if the carbon dioxide came from very old hydrocarbon or oils or from naturally occurring things that are more recent. Here's Dr. Boyd explaining the sampling method for carbon trapping in the field.
Well, the way we do it is we have a system that we put in the current project into existing groundwater wells. And so the wells have a screen in the water in the saturated zone, and any CO2 that diffuses into the well casing, we collect by adding a series of tubes that go into the well. The one tube collects right at the water air interface within the well casing, and the other is a return line. The material in the gas in the headspace is pumped out and through a CO2 trap, sodium hydroxide, and then fed back into the well casing. And so you're not pulling something out and artificially drawing the volume of gas out of the system, but you're scrubbing the CO2, which creates an equilibrium of CO2 coming from the groundwater into your trap, and then that trap material can be analyzed for both the radiocarbon content to determine how much of it's coming from the hydrocarbon or the contaminant, as well as the rate at which it's produced, so the respiration rate of the organisms in the groundwater.
That sounds really neat. It sort of reminds me of the movie Apollo 13, where they're searching for these carbon scrubbers. Similar technology and chemicals?
Poonam, I had the same thought and asked Dr. Boyd about this. And he said, yes, that's carbon dioxide scrubbers or sorbers, the same technology is being used in his approach.
Well, I guess great minds think alike. Now, do you know how long the test runs for?
Well, yes. After several trial runs, it was determined that a 1-month trapping period is a reasonable time frame logistically and scientifically. Now, here are a couple of additional photos showing the field setup. The lower middle photo shows some of the valving used to collect the groundwater for trapping, and the photo to the right shows the solar panel used to drive the pump, shows the traps and other equipment. Now, following the completion of the radiocarbon analysis, a computer model is applied using site-specific hydrogeologic data. This model is used to determine the zone of influence of where that CO2 is extracted from the aquifer around each monitoring well. The figure to the right shows a zone of influence map for one of the monitoring wells, where the red indicates little removal of CO2, and the lighter colors show high removal rates immediately around the well itself. The zone of influence data is then combined with the radiocarbon results to determine how much TCE is being biodegraded in units of grams per day of carbon within a cubic meter of aquifer material. Now, this map shows the interpolated TCE biodegradation rate across the plume based on the monitoring well data. It's labeled as chlorinated hydrocarbon turnover, where the red color signifies higher biodegradation rates and the blue color shows lower rates. Now, when these results were applied across the entire dissolved plume, the overall biodegradation rate was calculated to be about 90 kilograms of TCE and other chlorinated solvents per year, or about 200 pounds per year in English units. Now, that's quite a bit for this groundwater plume that's estimated to be a total of 1,500 kilograms of dissolved chlorinated solvents, so that if there's no DNAPL source materials feeding this dissolved plume, then it would take about 17 years for these natural biodegradation processes to remediate the plume. Not too bad.
It's also worth stating that since the sampling is done at monitoring wells that are already installed, this is an easy way to continue monitoring the TCE plume without expensive repeat sampling and helps us take the guesswork out of areas to prioritize for remediation. This project is in the R&D stage, but stay tuned to see how this technology will be demonstrated and validated in different plumes other than TCE and in different hydrogeologic settings. Dr. Boyd has just been awarded a follow-up project with his research partners, eFlux and GSI Environmental in 2018, so we'll be hearing more about this technology in the future.
Sounds good, Poonam. But now let's wrap up by going over those key points and findings again.
Sure. So understanding the natural biodegradation rate of chlorinated solvent plumes is very useful in managing these plumes.
Now, a new method based on using radiocarbon analysis and carbon dioxide flux measurements has been developed and tested in the field.
At the test site, the method showed 90 kilograms per year of chlorinated solvents that were being biodegraded naturally over the entire groundwater plume.
And that's a lot compared to the estimated 1,500 kilograms of chlorinated solvents in the dissolved plume, and suggests the plume might be largely biodegraded away in 17 years as long as there are no other source materials like DNAPL in the subsurface.
Now I'd like to direct our audience to the CERDIP ESTCP website at cerdip-estcp.org, where you can find more information about this project. And remember that this is one of a number of CERDIP and ESTCP project summaries here on the CERDIP ESTCP channel. Just go to YouTube and search CERDIP/ESTCP micro lectures to see more of these short, focused, graphical project summaries and meet the PIs who actually did the research.